everyone. Anyone who will get the cue? When are you getting your results? Sir. Nice. What is the last subtopic we have done? Electric. Hi, good morning, people online. Can you hear me? People online, hi, can you hear me? Hello. Okay. Right. What is the last subtopic? Electric field strength. Yeah. Electric potential. Sorry. Electric potential. I have given you a question for homework. Yes. The question number 2. I have told a particle of charge 50 microcoulombs is moved from A to B. The diagram is given. Calculate its change in electric potential energy. Correct? So just to recall, what is electric potential? It is the amount of work done per unit charge when bringing a small positive charge from infinity to that point. Am I right? So guys, from a charge Q at a distance R, the electric potential is given by 1 over 4 pi epsilon naught Q over R. 1 over 4 pi epsilon naught is a constant, where epsilon naught is the permittivity of free space. Correct? And 1 over 4 pi epsilon naught is 8.99 into 10 to the power minus 9. Correct? So that is electric potential. So what is electric potential energy of a charge at a particular point? It is the product of the electric potential at that point multiplied by the charge which is kept at that point. Correct, right? Fine. So guys, the particle is moving from the particle of charge 50 microcoulombs is moving from point A to B. So point A is a point to 20 centimeters from a 2 coulomb charge. And point B is a point which is another 10 centimeters further away from A. So the question is to find when you move a charge from A to B, a 50 microcoulomb charge from A to B, what is the change in electric potential energy? Correct? So guys, electric potential at A will be, VA will be 1 over 4 pi epsilon naught 2 over 0.2. Correct? Electric potential at A. Electric potential at B will be 1 over 4 pi epsilon naught 2 over 0.3, because the distance from 2 coulombs to B is 0.3 meters. Agree? So guys, the potential difference between the 2 points, delta V will be VA minus VB, which I can take it as 1 over 4 pi epsilon naught 2 over 0.2 minus 2 over 0.3. This is a potential difference. I will denote it as delta V. Agree? So which means the potential difference is 1 over 4 pi epsilon naught 2 over 0.2 is 10 minus 2 over 0.3 is 20 over 3 which is 104 pi epsilon naught 10 over 3. Can use a calculator. This is the delta V. So the electric potential energy change will be, I will take it as delta E. This 104 pi epsilon naught into 10 over 3, which is the potential difference, multiplied by the charge. What is the charge that you are moving? 50 microcoulombs. 50 into 10 to the power minus 6. Correct? Now tell me what is 104 pi epsilon naught? 8.99 into 10 to the power? 10 to the power 9 or minus 9? 9. Into 10 over 3 into 15 to 10 to the power minus 6. That will be 1.50 into 10 to the power 6 joules. Is that okay? Have you got this answer? Yes or no? Now guys, tell me this. Now I asked you for the change in electric potential energy. Now when you move the charge from A to B, will the electric potential energy increase or decrease? When you move the charge from A to B, will the electric potential energy increase or decrease? Yes, I want an answer. Huh? Decrease. Why? What do you think? Increase. Decrease. Why? Yeah, moving away, right? So when you're moving away, the electric potential will decrease. Yes or no? Because potential is inverse proportional to the distance. Right? V is 104 pi epsilon naught Q over R. So V is inversely proportional to the R. So when you move away from the charge, electric potential is decreasing. Okay. So the electric potential is decreasing. The electric potential energy is decreasing. So actually, this final answer is supposed to be minus. So I'll give a minus sign just to indicate that it is a decrease in the potential.
So could you explain again why is it minus or answer?
The electric potential is V is 1 over 4 pi epsilon naught Q over R, right? So that means from a point charge, V is inversely proportional to the R. Correct? As the R increases, electric potential will decrease. So when you are moving from A to B means you are going away from the fixed charge. That means you are going to a lower potential point. So you are going to a lower potential point means the electric potential energy will decrease. When you come towards the charge, electric potential energy will increase. Is that okay? Right? Did I ask you to do anything from the tube? Any questions from the tube? Right, guys, write down the subtopic: electric field lines and equipotential lines. Electric field lines and equipotential lines. Right. Now, guys, electric field lines means the lines which is used to represent the electric field. The name itself suggests electric field lines. The lines which are used to electric field, they represent the electric field. And the electric field, listen to me. Electric field, the direction of the electric field is the direction in which a positive charge will move, or a positive charge will experience a force. Okay. Now, guys, if I take a positive charge, the electric field lines around it will be away from the positive charge. Do you agree with me? From a positive charge, the electric field lines will be away from it. Why? The reason is, look at this. Let's say I take a positive charge and keep it here. Okay. There is a positive charge here. And at this point, I keep a small positive charge. It will experience a force which way? Away, right? Due to this positive charge, the positive charge I keep here will experience a force away, right? So which means the electric field line at this point will be away. Understand? So the easiest way for you to remember which way the electric field lines will be, you just think at that point, if you leave a +1 Coulomb charge, or if you leave a small positive charge, which way will it experience the force? So that way is the direction of the electric field. Understand? So basically, if you take a positive charge, the electric field lines will be away from it. Okay. If you take a negative charge, it will be very similar. The only difference is the electric field lines will be towards the negative charge. Okay. Why is that? Once again, if I leave a +1 Coulomb charge here in this field, it will experience the force towards the negative charge. So that means the electric field lines are towards. Is that clear? So remember the basic of electric field lines. It will be away from a positive charge towards a negative charge. Right, now listen. That is about electric field lines. So the heading says electric field lines and equipotential lines. What is equipotential? Equipotential. Huh? I heard it. Equal potential. Equipotential means equal potential. So the equipotential line means it's a line which connects the points which equal potentials in the field. Okay. Equipotential line, it's a very simple thing. A line or a curve which connects the points with equal potential in the field. So for an example, if I go back to this one, at equal distance, now since this is a positive, just a positive charge, equal distance from this charge, the potential will be the same, right, at these points. Okay, so this will be an equipotential line. Okay, and if I take at these distances, again equal distance from the positive charge, the potential at those points will be equal. So that will be again equipotential line. So for a positive charge or a negative charge, it will be basically a line which is with it's basically a radius. You can draw any number of equipotential lines. So at equal distance, the potential will be equal. So the line which connects, or the curve which connects those points, is what you call a point. Equipotential line. Can you please take it down? Mark the equipotential lines with a dotted line. Okay, done. Okay, right, guys, what if it is, look at this. If you take a positive charge and a negative charge, if you take a positive charge and a negative charge, look at this one. The electric field lines will be away from the positive charge towards the negative charge. These are the electric field lines. And that field lines will be perpendicular to the charge. When it is moving away from the charge, it should be perpendicular to the charge. So it will be towards the negative charge. And away from the positive charge. Okay. When it is leaving away from the charge or coming towards the charge, remember that the field lines have to be perpendicular at the surface of the charge. First, draw the field lines. Draw only the field lines. I run with the field lines. Don't draw the potential line, only the field lines. That is, one is positive, the other one is negative. Okay. Right, guys, what if both are positive? Look at this one. If both charges are positive, and one thing about these electric field lines, when you're drawing, make sure there's two electric field lines will not cross each other. If you look at this diagram, you can see two field lines will not cross at any point. Okay, so check your diagram. You can't have any field lines which are crossing each other. Okay, right. So if both charges are positive, it will be away from both the charges. It will be, the field lines will be away from both. Okay, look like this. Tell me about this point. Will there be a field line at this point? Will there be a field line at that point? No. So then, at that point, is there an electric field strength? No. What is the electric field strength at that point? 0. You call it a neutral point. Okay. Take it down. Only the electric field, don't draw the potential lines.
So which are the potential lines?
The dotted lines are the potential lines, don't draw that. Okay.
Yeah, okay. Done. Yeah. Ah.
Okay, guys, write on the next subtopic. Capacitance. Capacitance.
So aren't you going to write any notes on electric field and equipotent lines?
Not really. Do you want?
Yeah.
Oh, wait, before we move on to the next, we'll do a question. Question number 12. Next, question number 12, part B. Can you do 12 part B? Use a pencil. Hello. I'll keep your battery. Okay, question number 12. Alpha particles were chosen by Rutherford for large angle scattering experiments. Okay. Part D, we'll come back to that later. Part B, the scale diagram shows two equipotential lines in the electric field around the gold nucleus. Sketch lines to show the electric field between these two lines of equipotential between these two. So where is the electric? Now, this is a positive, listen, don't draw this agree. The positive, the nucleus is positive, right? Nucleus consists of protons and neutrons. Neutrons are neutral, so protons are positive, so the nucleus is positive. So guys, the electric field lines will be away from the nucleus. It has to be this way. Yeah. But the question is to draw the electric field lines between these two equipotential lines, not from the charge itself. not from the nucleus itself. It is to draw between the field lines. So it has to be which will be directed towards the center. This is how the field lines will be. Okay, it should look like it is coming from the center. Sorry. Okay, right. And the next part. The 40 volts line is drawn to scale correctly, given to the correct scale. Deduce whether the 10 volt electric potential line is in the correct scale position. Guys, answer to me. Now we know V equals 1 over 4 pi epsilon naught Q over R. Okay, which is V is inversely proportional to the R. Okay, so guys, now listen to me. Now here, this is the nucleus. Here the potential is 40. Here the potential is 10. Any baby will know 10 is 1/4 of 40, right? Okay. So comparing to this level, here the potential is 1/4. So for the potential to be 1/4, the distance has to be 4 times. So which means if this distance is x, this distance should be what? 4x. Correct now? So they are telling you that the 40 volts is perfectly fine. It is given to a scale. So all you need to do is check this distance, measure this distance. Okay. And then measure this distance. If this distance is 4 times this distance, then yes, 10 volts is at the right point. Otherwise, no. You understand what I'm saying? The question is, deduce whether the 10 volt potential line is in the correct scale position. It is at the correct position. So if this is the 10 volts, when this is the 40 volts, this distance from the center of the nucleus to 10 volts should be 4 times the distance from the center of the nucleus to the 40 volts. So can you first measure the distances? According to your diagram, from the center of the nucleus, can you tell me, measure and tell me, from the center of the nucleus, what is the distance to this 40 volts? 0.8 centimeters. Can you measure from the center of the nucleus to 10 volts? What is the distance? 0.9. Okay, let's say 0.9 centimeters. What is the distance from the center to the 10 volts? 3.8 centimeters. So 0.9 into 4 times is how much? 3.6. So 3.8 centimeters is pretty much okay, because there can be errors with your measurements as well. Sometimes when you have measured 0.9, it can't be exactly 0.9, it can be something between 0.8 and 0.9 as well. So, or maybe it can be slightly more than 0.9 as well. So I would say yes. Yes. And I will give you my reason. The distance from the distance from center of the nucleus to plus 10 volts line is 4 times the distance from center to plus 10 volts line. Is that okay? That's how the sorry, plus 40 volts. Right, there's the next one. An alpha particle moves from plus 10 volts potential to plus 40 volts potential. Calculate the increase in potential energy of the alpha particle in electron volts. First tell me this. Guys, an alpha particle consists of what? From your O levels, you remember. An alpha particle consists of 2 protons and 2 neutrons. Correct? So guys, anyway, the 2 neutrons don't have a charge, correct? So basically the charge of the alpha particle is a charge of 2 alpha particles, charge of 2 protons. So the charge of the 2 protons will be 2 into charge of a proton is 1.6 into 10 to the minus 19 coulombs, if you can remember. Anyway, don't worry, this data is there in the data sheet. So 2 into charge of a proton, that is 3.2 into 10 to the minus 19 coulombs. Okay. These are charge. Now guys, if you are moving an alpha particle from plus 10 volts to plus 40 volts, what is the potential difference? Potential difference is 30 volts. This is similar to the first question that we did today, going from one potential to another potential. So the gain in electric potential energy will be that potential difference, which is 30, multiplied by the charge, which is 3.2 into 10 to the minus 19. How much is that? 9.6 into 10 to the minus 18 joules. Is that okay? Any questions? You can ask me a question. Ask me. Sure. So gain in potential energy will be the potential difference multiplied by the charge.
So how is the charge 3.2 enhancement?
Because an alpha particle means 2 protons. Alpha particle consists of 2 protons. Okay.
Yeah.
So 2 protons is 2 into charge of a proton is 1.6 into 10 to the minus 19. Is that okay?
Yes.
Right. Wait, but that's not the final answer. Line up. We want the energy in what? Electron volts. How do you convert joules to electron volts? Divide by the charge of an electron. So 9.6 into 10 to the power minus 18. Again, we need to divide by charge of an electron, which is 1.6 into 10 to the power minus 19. How much is that? 60 electron volts. That will be the energy gain. Right. Guys, you know the Cambridge students got their results day before, right? Did you check it? No?
So,
You didn't? Yeah.
so this is the potential energy for one proton.
No. This is for the alpha particle.
Why? No, why do you divide by 1.6 times 10 to the power minus 19?
That is to now here we got the energy in joules, right?
Yeah.
So to convert joules to electron volts, we divide it by the charge of an electron, right?
Yes.
If you want to convert electron volts to joules, you multiply by the charge of an electron. If you want to convert joules to electron volts, divide by the charge of an electron. If you didn't know about it, make a note of that. How to convert electron volts, I mean joules to electron,
What about it?
divide by the charge of an electron. Okay. Any questions? Right. Then right, guys, question number 19, give a time. Question 19. Question 19. Right. Question 19. There is an electric field around the helium nucleus. Calculate the electric potential at a distance of 26.6 into 10 to the power minus 12 meters from a helium 2,4 nucleus. So guys, the helium nucleus consists of what and what? 2 protons and 2 neutrons. So use your common sense and tell me, what is the charge of a helium nucleus? It will be 2 into charge of a proton, which is 2 into 1.6 into 10 to the power minus 19. That's 3.2 into 10 to the power minus 19 coulombs. Am I right? So the electric potential at a distance of the given will be 1045 epsilon naught into Q is 3.2 into 10 to the power minus 19 over the R is 26.6 into 10 to the power minus 12. Am I right? Yes. Can you please tell me the value? 108.1. 108.1 volts. Sorry, 108 then. Okay. Yeah. Since the unit is not specified, you can either give joules per coulomb or volts, both are correct. Right. Step 1, assumption made for this calculation. What is the assumption that we have made? Why? Yeah, there are no other charges around it. Correct, that is one assumption. Or another assumption, we can say guys, this gold, what nucleus? Helium nucleus. Helium nucleus is a point charge. Because this equation we use it from a point charge. So we assume it to be a point charge. So you can write that as an assumption. Helium nucleus is a point charge.
So what do you mean by point charge?
Wait, helium nucleus is a point charge. So this is a point, this is not a point. Correct? No? Yusuf?
Yes, sir.
So we are assuming that it's this, it's concentrated to a point, not spread in a large area. Okay. Because this equation is for a point charge. But whenever we apply this equation, we assume it to be everything to be a point charge. Okay. Right. Well, now in the last two diagrams that you did draw the electric potential lines, right? I want you to draw it now, but you have to be very careful. Look at this one. I will explain it. After that, you can draw. Listen to me. But you don't have to draw this many lines, okay? This is too much. If you draw about 6-7 lines, that's enough. Or maybe 5 should be enough. Now listen. I will explain it to you. Now, One is the positive charge, the other one is a negative charge. So once again, equipotential means the line which connects the point with equal potential. Okay. That's great. Guys, I will take one equipotential line, which is this one. Okay. Does it look like a circle for you? No, it's not. It's more of a slightly an oval shape. And anyhow, the point to notice here is the right hand end of this circle is closer to the charge compared to the left hand. That is a significant thing to notice. I will tell you why. Okay. If you can understand why, it's easier for you to remember. I'll take this one. Okay. Now, this minus charge is also there. This negative charge is also there. Okay. So that negative charge will also contribute to the potential around this positive charge. So now if you take a point somewhere here, the potential at that point is due to both positive charge and negative charge. Okay. If you take this point, the potential here is due to the positive charge and the negative charge. But if you take a point on this side, it is less affected by that negative charge. Let's say it's not affected by the negative charge, or the effect is very less. Okay. So now to have the same potential on either sides, do you understand the point on this side has to be closer to the positive charge compared to the point on the other side? Think about it. Okay. Listen to me. Now guys, I will take a few numbers and explain it to you. Now assume this negative charge was not there. It was not there. Okay. Listen to this part. If that negative charge was not there, let's say from the positive charge at a certain distance, from the positive charge at a certain distance from here to here, the potential is, let's say, 10 volts for an example. This is, I'm talking if the negative charge was not there. Then even on the other side at the same distance, it will be 10 volts. Correct? It will be 10 volts. If the negative charge was not there, on both the sides at equal distance, the potential will be the same. Now, because the negative charge is there, when the negative charge is there, this 10 becomes 7. But that negativeness is contributing to this point. The negative charge is having a potential at that point. So it will reduce the positiveness of this point. Okay. So now from this positive charge on either sides at equal distances, here the potential is 10 volts, here the potential is 7 volts. Okay. So which means on this right side here, to get the same 10 volts, you have to get closer to the charge, right? You want to get the same 10 volts on the right side of this positive charge, you have to get closer to the positive charge. Understand? So the summary is, let's say there exists a point from the positive charge on the left side, the point with 10 volts. To have the same 10 volts on the other side, it definitely has to be a point closer than that. Agree? I hope some of you understood it. Some of you didn't understand. Those who didn't understand, go home and give a thought about it again. Think about it again. If you still don't understand, just remember this. This is how it is. Okay? No, because it's not a big thing, right? The verse they can give you in a question to draw it. So if you know how to draw it, that's fine. But the reason why I explain it so much is for a person who can analytically think, logically derive this, you don't have to memorize it. You can just think and draw it. But if you think you can't do it, just memorize it. Simple. So something like this. Yeah.
So first of all, that's what I told for notes. And sir, does equipotential mean, is it according to the distance or the strength? Equipotential. Is it the distance? Is it the distance from the nucleus or the
potential from the nucleus? Equipotential means the points where the potential is equal.
Okay,
so if you
not the
take
distance.
no, distance doesn't have to be equal. That's what this is a classic example of that. Okay, in this example, you can see here these points are close to the positive charge. Just to have the same potential on the other side, it's far. Okay, so guys, no need to draw all. Just draw about 4 or 5 lines. But when you are drawing, make sure every single line that you are drawing is this side is closer to the positive charge. This side is further from the positive charge. So the same thing applies on the other side as well. You see, for the negative charge. Listen, this side will be closer. This side will be away. These are the equipotential lines. Understood?
Yes, sir. So you told the electric field line should be away from the positive side.
Yes, I was also about to tell that.
Just
towards the
ignore the field lines in this diagram. This is wrong. Just don't copy the field lines from this. Anyway, you are done with the field lines. Only mark the potential. Just don't look at the field lines in this. Do you want me to draw it? Or can you look at copy from this? Okay, guys, and one more thing for you to notice. At each point, if you look at this diagram, this equipotential line will be no, let's draw it. Done, right? Guys, for the next one, let's say both are positive. So when both are positive, the diagram is the other way around. Okay? Which is, if I take one field line, if I take one field line like this, one potential line. On this side, the distance is more comparing to this side. Okay. For the very same reason, I'm not going to explain it and confuse some of you people. Okay. So here also on this side, this draw it in a way. Now this part side will be closer compared to this one. And I hope you remember I told you, in this region, the electric field strength is 0. So the electric potential will be 0 and there will be no equipotential line there. Done. Right, take that here. Right, guys, question number 1. Can you give it a try? I'll give you 5 minutes. Read the question properly, yeah? Read the question properly. Please keep your phones off or put it to silent. Yeah, people listen to They didn't ask you for the 3 lines on the potential. Do the pencils. Have you taken it? Yeah. Do the pencil. How many field line potential lines needed? Minimum 3 needed. No? Because they are asking to show that add lines to draw that to show equipotentials at intervals of potential difference. No? The minimum 3 will be needed. But unfortunately, every single diagram I checked is wrong. Yeah. Now listen to me. Now listen to me, people. The intelligent people, listen to me. Okay. Right. So what everyone did is add lines to the diagram to show equipotential at intervals of equal potential difference. You saw it, and you drew a circle from point X with a certain radius, and you double that radius and you drew another equipotential line. Okay. If you want another one, what you did is you triple that radius and you drew another line. So let me explain the math behind this. Listen to me. Guys, now according to what this diagram says, if this distance is r, thank you, this is 2r and this is 3r. This is what you did, and what I'm saying is wrong. The reason is, my dear, listen. Guys, if by any chance, if the potential at this point is 100 volts, okay, at a distance of r, if the potential is 100 volts, you tell me at 2r what is the potential? 50. Correct, no? Because the potential is inversely proportional to the r. Okay, listen to this carefully. Don't make this mistake, okay? But don't memorize it, understand. Very logical subject. So guys, if you double the distance, potential becomes half. Simple math we have been learning from grade 9, variations. The inverse proportionalities, inverse square proportionalities, you learn for grade 9 maths. You learn that to apply in future, not for fun. So this is the future of that pass. So guys, when you double the distance, the potential becomes half. Now when you triple the distance, potential becomes 1/3. So if the potential here was 100, here the potential will become 33.3. Am I right? So now tell me, here the potential difference between these two levels is 150, 50 volts. Here 50 and 33.3, 16.6 volts. Is it equal potential difference? No. Do you understand what I'm saying? If you take equal distance and draw equipotential lines, it won't result in the equipotential lines with equal potential difference. What are they asking you to draw is equipotential lines in such a way the potential difference between adjacent equipotential lines will be equal. Read the question again. Add lines to the diagram to show equipotential at intervals of equal potential difference. Understand? So if you do it this way, if you take the potential at this point to be 100 volts, potential at this point will be 50 volts, potential at this point will be 33.3 volts. For an example. So here the potential difference between these two will be 150, the difference is 50. Between the next two, the potential difference is 50 and 33.3, 16.6. So that won't result in what? Equal potential difference. Understand? So if you want equal potential difference, you can't make the distance between the equipotential lines equal. Okay. Then tell me, what should you do? Okay. Now tell me, I'll remove this fellow. Okay. Let's say this is my first equipotential line. Okay. And let's say this is my second equipotential line. Now tell me about the third one. What should I do? I'll give you two options. One is this one. One is this one. Which one is the right one? I label it A and B. Which is the right one?
Definitely B, sir.
Which one?
B.
Which one? B. So that means in the early example I took, guys, between the first and the second one, the potential difference was 50. 150 and 16.6 or something. So between the first two, 50 means to get the same potential difference between the other two, the next one you have to take it further away. Understood? So it has to be in such a way the distance between the first distance between the first potential line and second potential line is certain distance way. Distance between the second potential line and third potential line has to be even more. I mean, I don't want quantities. I mean, we don't have to give numerical values. Just the fact that you have to show it's a true marker. Obviously, they don't look at values here. Just to check that you understand the fact it's not equal distance and distance has to increase. Now, please don't they make this mistake again. Right, do the part B. There's a charge of minus 4.5 nanocoulombs is placed 4 centimeters from X. Calculate the magnitude of the force acting on this charge due to the charge at X. The charge at X is 7 nanocoulombs. So the force will be, guys, 104 pi epsilon naught Q1 Q2 over R square. Okay. So 104 pi epsilon naught is 8.99 into 10 to the power minus 9. Q1 Q2 4.5 into 10 to the power minus 9 to convert nanocoulombs to coulombs into 7 into 10 to the power minus 9 divided by R square, which is 0.04 square. Here we are the 10 to the power 9 here. So what are we getting? 1.8 into 10 to the power minus 4 newtons. Straightforward. Okay. The next one, the minus 4.5 nanocoulomb charge is moved from a distance of 4 centimeters from X to a distance of 9 centimeters from X. Calculate the work done on the minus 4.5 nanocoulomb charge. So guys, the 7 nanocoulomb is here. The 7 nanocoulombs is here. And from there, 4 centimeters away, you have the minus 4.5 nanocoulombs. Okay. Minus 4.5 charge is moved from a distance of 4 centimeters from X to a distance of 9 centimeters from X. So that means from here you move this charge a further 5 centimeters. Correct? It's moved from here to here. Right? So the question is, calculate the work done on charge minus 4.5 nanocoulomb. So work done is equal to the electric potential energy it will be gaining. Okay. So we have to see the potential difference between these 2 points and multiply by the charge that is moving. That will be the work done. So guys, the potential at, I'll take this point to be A, this point to be B. So the potential at A will be 104 pi epsilon naught 7 into 10 to the power minus 9 over the distance is 0.04. Similarly, potential at B, VB will be 104 pi epsilon naught. Okay. 7 into 10 to the power minus 9 over the distance is 4 plus 5, 9 centimeters, which is 0.09. Okay. So the potential difference will be V delta V, VA minus VB. I'm getting 874 volts. Correct me if I'm wrong. So guys, the work done will be 874 multiplied by the charge that you are moving, which is 4.5 into 10 to the power minus 9. That is 3.9 into 10 to the power minus 6 joules. This is the work needs to be done. Sorry? This charge is 7, right? So this is a fixed charge. From that fixed charge, I first found the electric potential at a distance 4 centimeters. Then I found the electric potential at a distance 9 centimeters. We already did a couple of questions similar to this today.
So why aren't you multiplying by minus 4.5 instead of plus 4.5?
Guys, don't take the sign into account here. Okay, whether it is minus or plus, you don't take the sign into account when you're doing the calculation. So that minus plus is for you to understand whether the forces are attractive or repulsive, or whether you have to do the work or work is done by the field. That you don't take it into calculations. Okay. Any questions, anyone? Do you want a break? See you in 15 minutes.
So Ansukam, what is the formula used for work done?
Work done is the potential difference multiplied by the charge that you are moving, right? Potential difference between the 2 points multiplied by the charge.
Sir, why did you convert 4 centimeters to 0.04?
Normally we use meters, right, in calculations.
Okay, guys. Question number. Question number 5, a baby question. Okay. The diagram represents a negative point charge. Draw field lines to show the electric field around the charge. This is a question like even your, yeah, come on.
Be towards it.
They are nice like that. This is actually even your grannies can do this. Seriously. Huh? What was it? What did she do? Still they can do. So guys, the field lines will be towards the charge. Okay. So guys, it will be directed towards the negative charge. Done. That's it. Question number 6.
That's also.
Yeah, for that question, that's also.
Nice.
Yeah, they are only asking for the field lines to show the electric field.
And we
around the
get 3
charge.
marks for that.
I'm not very sure. One will be for the direction, one will be for the pattern. I mean, the field lines, straight lines. Yeah. Do this, you will get the 3 marks. Question 6. And before I forget it, guys, next Saturday we have the class as usual. The week after that we don't have the class. So obviously then next week we have a cover-up class. So I was initially thinking to have it on Friday in the morning. Okay. But then
What Friday morning?
this coming Friday, next Friday.
No, sir, please. Not Friday, sir.
Why?
Sir, it's hard for me, sir.
Okay. Okay. Anyway, initially I was thinking Friday because. Okay. What if I tell Tuesday morning?
Yeah, okay. Deal, yes.
I believe you all have school holidays.
But we have chemistry and physics. I mean, biology.
You don't have school holidays? You don't have school holidays? Who is having school? Who is having school next week? You have school? Oh. Okay. Then Monday also you have school, right? Friday do you have school? When are you getting school holidays then? When? Only one. Next Saturday we have the class. Okay. So guys, then it will be on Friday. Okay, we have to have one of those days. Oh, what about tomorrow then? Can I
Yes,
spoil
sir.
your
Yes, sir. Yes.
Yes, yes,
can I spoil your Sunday?
yes,
Yes, sir, please.
Huh?
Yes, sir.
Okay, wait. I will put a message in the group. Just stick to that. Right. Question number
Sunday
6.
it is.
Question number 6. Yeah, if you are not in the group, send me a message. And my number is this. Send me a message on WhatsApp. Because when you're sending a message, don't just send hi. By the way, how you have typed hi, I can't understand who you are. Okay, just mention your name and from which class you are. So when I tell students to send me a message on WhatsApp, they just say hi. And I should understand who is this man. Right. The first one is a nice one. The surface of a balloon can become charged by rubbing it against clothing. The charge on the surface of the balloon can be assumed to act as it was concentrated at the balloon's center. Two balloons are suspended by cotton thread so that they just touch each other, as shown in the diagram 1. The two balloons are then given an equal negative charge. They are given an equal negative charge and repel as shown in diagram 2. The dots represent the center of the balloon. Part A, part 1. Show that the force of repulsion between the balloons in the diagram 2 is about 1 into 10 to the power minus 3 newtons. The mass of the balloon is 1.1 grams. Aren't you doing? Guys, use your common sense and tell me what is the radius of the balloon? Zero 0.21 divided by 2. Correct now? From here to here, the distance is 0.21, which is from the balloon center to center. So the radius has to be half of that. How much is that? 0.105. The radius is 0.105 meters. Right. Look at this part. They are asking, show that the force of repulsion between the balloons. So guys, I will take one of these balloons and mark the forces acting on it. Definitely the weight is acting down. Mg. The tension from the string is acting this way. T. And the force of repulsion is acting this way. Let me take it as F. These are the forces acting on the balloon. Now this balloon is under equilibrium with these three forces. Correct? So guys, this is the string. I will take this angle to be theta. This angle to be theta, where the string makes with the vertical. No, don't try, just listen to me. If I consider the vertical equilibrium of a balloon, just recall your AS physics. If we consider the vertical equilibrium of the balloon, T cos theta equals mg. Am I right? And if we consider the horizontal equilibrium of the balloon, T sin theta equals F. Agree? If I divide the two equations, F divided by mg equals T sin theta divided by T cos theta. Am I right? F over mg equals T sin theta over T cos theta. We have done enough of these various levels. The T and T will cancel off. So F equals sin theta over cos theta is tan theta and cross multiply mg tan theta. That's going to be the F. We know the M. We know the mass of the balloon 1.1 grams. Obviously, we know the G. We don't know the theta. We don't know the tan theta. Okay? Again, simple math. Guys, let me extend this, my line here. Okay? This is what I told to as theta, right? Now, finding the theta will be a sport here. Can you copy up to this one? Okay. Right. Fine. Now let's find the theta. This will be a little bit of maths. Not very hard. Look at this. You can recall your O-level maths. Right? Let's look at this one. Stop your work. Let me extend this line. Okay. I have drawn a vertical line through the center. And let me do the same thing here as well. Now we know that this distance is 0.21 meters, right? Correct? 0.21 meters, right? Which means this distance is 0.21 meters, right? Don't write, listen to me. And also, guys, the distance from here to here, that is given in the diagram 0.47 meters, right? correct? 0.47 meters, right? So now, if I take this length to be x, okay, simple maths, x equals 0.47 minus 0.21 divided by 2, right? Which is 0.13. 0.47, 0.21, 0.26, 0.13. Yeah. So x is 0.13. The rest is simple trigonometry for this triangle. I know this length is 1.22 from here to here. Correct? So for this triangle, if I take sine theta, opposite over hypotenuse, sine theta is 0.13 over 1.22. So the theta will be sine inverse. Sine inverse 0.13 over 1.22, which is 6.1 degrees. So now coming back to the F equals mg tan theta. M is 1.1 grams, 1.1 into 10 to the power minus 3 to convert grams to kilograms. G is 9.81 into tan 6.1. 1.1 10 to the power minus 3 into 9.81 into tan 6.1, which is 1.15 into 10 to the power minus 3. Newtons. So they have given the answer to one significant figure. 1 into 10 to the power minus 3. No, they have anyway told, show that the force of repulsion between the balloons in diagram is about 1 into 10 to the power minus 3. They haven't told the exact value. So my value is 1.15 into 10 to the power minus 3 newtons. Done. Do you have any questions? You can ask. So
You can use it as MGDOL.
you can directly use it as
MGDOL.
mg.
DOL. D as in
The tan theta. Yeah. No. DOL is the sine theta. No, what you're taking is the L in that case has to be this length, no? That is not 1.22. What is given as 1.22 is this one. From here to here. This one. There's a small difference. You might be getting a very close answer, not the exact answer. You got what I think? How did the 0.21 meter come? 0.21 meter came from the diagram. Here it's in the original diagram. The distance between the two centers is given 0.21 meters. So that is the distance here. This is 0.21 meters. Okay. Can we move on to the next one? Right. Show that the charge on each balloon is about this much. So guys, now we can use F equals 1/4 pi epsilon naught Q1 Q2 over R squared. So that is the F is guys 1.15 into 10 to the power minus 3. (104 pi epsilon naught is 8.99 into 10 to the power 9. Q1 and Q2 both are the same. So I'll take it as Q and Q square, Q into Q. Over the distance between the two charges is this one, which is 0.47. 0.47 square. And to get the Q subjected from here. I'm getting 1.68 into 10 to the power minus 7 coulombs. So the question was to show that it is about 2 into 10 to the power minus 7. Yeah. 1.67 into 10 to the power minus 7. Right. The next one is so easy. One balloon is removed and the remaining balloon returns to its original position. Calculate the electric potential at a distance of 0.3 meters from the center of the remaining balloon. So just a matter of using the equation. That is 1/4 pi epsilon naught Q over R. So now the Q is 1.68 into 10 to the power minus 7 over the R is 0.3 meters. I'm getting 5,040 for 3 significant figures. Yeah, I got 5,037.3. That's because I think you would have used 1.68 into 10 to the power minus 7 for the charge. I used the actual value that I got from the previous part. Okay, that's okay. Just stick to whatever the value you are getting. Is that okay?
So I don't understand the B parts. What's happening?
We are just using this equation.
No, I mean, like, what's happening? Could you show the diagram of what's happening?
They are telling now the charge is here, balloon is here. It has come back to its original position. From here at a distance of 0.3 meters, There is a point somewhere here. They want to find the electric potential. That's it.
Ah,
Previous question to the radius. Why do we say 0.47 instead of 0.1?
Sorry, come again.
Why do we say 0.47?
You mean the distance between the charges? You are asking about this R, is it? That's not the radius. 104 pi epsilon naught Q1 Q2 over R square, the Coulomb's law. That R is the distance between the two charges. Yes. Right, guys, mark a few questions for homework. Guys, question number 17, we have done the part A. Please complete it. Question number 17, we only have done the part A. Complete the question. Yeah, that's all. So we'll continue from this point on the next day, and the next class will be before next Saturday. Okay, before next Saturday, we are having another class definitely. I will confirm the exact date within the day, most probably in the group. Okay. Bye, guys. See you. Take care. See you soon. You're welcome. Bye. See you.